Well, thanks for coming, everyone. And as the title suggests, this talk is going to be kind of a sequel to the talk I gave in Seattle in 2005. It was right before I started this, my first, my tenure track position at Wisconsin, where I still am, and right before my first child was born, and my son is now going to turn 20 in September, which is crazy. And yet I'm still thinking about homological stability and arithmetic statistics. So I want to kind of give a progress report on what's been happening in that area, some of my own work, but then also a lot of work by a ton of other people, many of whom are here at this conference. So I hope maybe this will sort of spur some discussions if you're interested in some of the results of the many people that I mentioned. So let's start with this question. Okay, this is supposed to be the session about connections between algebraic geometry and topology, and it is going to be, but this is a talk about that and about algebraic geometry over global fields. So I suppose I'm going to sort of talk about both of those things. And so this is a basic question about rational points on a variety. By the way, I should say this talk is going to be very light on details. I hope that's okay. I'm going to try to give a sort of global picture of this kind of line of work and this strategy of how it works. So if people have questions about the details, please ask. Because I'm on slides and I don't have a board, I might not actually be able to answer, but I'll sort of say some words that indicate what's hiding. Okay, so this is not a great answer because, as you probably know, projective space has infinitely many rational points. So the standard thing that we do in arithmetic geometry is to constrain this until it's a finite set, to say we're just going to look at the rational points of height at most b. And to start with no details, I'm not going to put up the definition of what height means over a general global field, but over Q, it's very simple. It just means you write down the coordinates at this point, which can be expressed as a list of n+1 integers, and you should make sure they have no common factor. And then the height is just the maximum of those integers. So that's very clearly a finite set. And then if you want to count how many there are, well, you have n+1 integers, and each one is of size at most b. So that seems like it should be b to the n+1. And indeed it is. The only extra content here is that, well, I did have this arithmetic condition that they're relatively prime. And it's not hard to show by relatively easy analytic number theory that that happens with a positive probability, neither 0 nor 1. And so you end up with some constant times b to the n+1. So there, we answered a question. More generally, we can ask this same question, but now for some projective variety. So another way to say it is, out of those b to the n+1 points, maybe I have in mind as a hypersurface some equation, and I want to know how many can satisfy that equation. Or it's not a hypersurface, it's a complete intersection or something, maybe some set of equations. Of course, if I have too many equations, then maybe I don't have any rational points at all, or maybe I have very few. And for the context of this talk, we're always going to be talking about situations where there's lots of rational points. And it turns out that a good criterion for this, we sort of want to say, for those who like curves, which is most of us, it's more like a rational curve than it is like a higher genus curve. And a good way to say that is to require that the variety be Fano, that is, that its canonical bundle is anti-ample. And we can ask again, how many points does X have of height at most b with bounded coordinates? And there's a remarkable conjecture that's been around for a lot longer than 20 years, the Batyrev Manin conjecture, which says, I should emphasize, we're not going to get an exact answer to this question. No hope of that. That's not really what we're looking for. We're going to ask for the asymptotic rate of growth. And the general belief is that this number grows like some constant times some power of b times some power of log b. And what these constants are, I'm not going to tell you, but there's a very precise recipe in terms of the geometry of this variety. The hardest part is specifying c. That's the part that Peach did. We'll say a little bit about constants later, but I'm not going to tell you what they are. I'm just going to tell you that there is a conjecture to this effect, that this function has a nice regular behavior that is governed in some way by the geometry of the variety. And this is the first of many times I'm going to sort of slightly lie. So for the fans of Batyrev Manin, I'm not going to talk about accumulating subvarieties. I'm not going to talk about thin sets. I'm just going to say sort of stuff that's generally correct to give you guys ideas about what's connected to what. I mean, you're allowed to yell out that I'm lying about something if you feel it's important, but just know that I know I'm doing it. So people have worked on this conjecture for a while. people know a decent amount. I'm not going to really go through these, but I'm just sort of giving you this list. And actually, this list, it's not meant to be up to date. I actually copied this from my notes from 2005 because we're sort of time capsule. So more is known now, but like maybe not as much as you might like. And in some sense, this is just to show you that it's rather special varieties where we can actually control the growth of rational points. And indeed, if somebody were to prove this theorem for a cubic surface tomorrow, which is like maybe we don't think of that as like a possibly hard variety, but that would be like a major advance that everyone would be very excited about rational points. And at the moment, we still just really don't know how to do this. And maybe because I'm going to talk about it a little bit later, I'll point out that there's one exception to these varieties being very special, and that's the very last item, which is of a completely different nature, that if you have just some hypersurface of a massive, massive dimension, and very low degree, like dimension, like exponentially large relative to degree, then you actually can prove this conjecture, and you can prove it by methods that are completely different from the algebraic geometry that takes place in the top half of the board. Then it's a question of analytic number theory. Then you can do it by the circle method, which is very, very good at studying solutions to equations. I mean, if you know any like British analytic number theorists, you know they like to sort of say like, well, let F be a form in like 19,000 variables or something like that. So it's like, that's the nature of the last bullet point, which is a bit different from the others. Okay. I haven't told you the analogy yet. I told you about sort of like one famous class of problems. The analogy is between that and this. Once again, I have some projective variety. And now I'm interested in, as an algebraic geometer, I might say the space of rational curves on this variety, the space of algebraic or even holomorphic maps from P1 to X. Because I said X is projective, right? So I don't have to sort of pay too much attention about the difference between holomorphic and algebraic, by contrast with what Jacob was just telling about this morning. I mean, the proper case. So yeah, there's like different things I could mean by this, holomorphic maps, or I could even be like incredibly soft and just say like, okay, I'm just going to think of the complex points of this variety as a manifold. And then I'm going to think of the complex points of P1 as a manifold. I'm enough of a topologist even to tell you what manifold it is. It's S2, the two-sphere. So maybe I'm just asking about maps, continuous maps from the two-sphere to the complex points of this variety, which is a topological question. So there's a philosophy in topology, which sometimes goes by the name of the Cohen-Jones Siegel conjecture, which is that if I look at holomorphic maps from P1 to this manifold, considered as an analytic variety, I can certainly take any such map and just forget that holomorphic structure exists. And just remember the topology and think of it as a continuous map. Those spaces are different. And this is sort of a part of what Mike was talking about in his lecture yesterday. I'll sort of quote him on this later. But somehow the philosophy is that as you let the holomorphic maps become a higher and higher degree, that space of maps becomes more and more like a space of continuous maps. Somehow a very high degree holomorphic maps from one variety to another, the space of such maps, you can almost like forgetting this holomorphic condition, and that becomes very similar in some homotopic sense to the space of smooth or continuous maps, which is more or less, just because it's maps from S2 to this manifold, it's more or less the double loop space of that manifold. And that's the kind of thing that topologists really can get their hands on and know a lot about. And I think this sort of story starts like 1979 when Siegel writes a paper about this, proving that this statement is correct when the target is a projective space. So studying maps from P1 to PM, the space of degree D maps from holomorphic maps from P1 to PM is just like lists of degree D polynomials. We can understand that very well. It's subject to some condition that non-degeneracy. And Siegel shows that as the degree gets larger and larger, that approximates the double loop space of Pn. And then Siegel comments that he's confident that, okay, I did it for Pm, but it would probably work for Grassmannians and flag manifolds too. And that turned out to be correct. Although, I mean, maybe the real topologists like Kirsten can tell me, I mean, this is kind of a long time, right, before these actually appear. It wasn't like 1980 or 1981. But by 2005, we did know that this kind of principle held in topology for a class of varieties. This general result was due to Boyer, Hertzsprung, and Milgram, which contains the other two cases. So I'm not going to talk about this in any detail, but what I want you to observe is that this list is kind of similar to the other list. And that's the starting point for the vague analogy. That in some sense, the varieties where we were able to prove something about material Manin are quite similar to the set of varieties where we were able to prove something about the space of holomorphic maps approximating the space of smooth maps. So,
is this list also from 2005?
Yes. Both of the lists I literally copied from my notes from that talk because I wanted it to be like historically accurate. So the question is why? What do these questions have to do with each other? And now we come to a quote I deliver all the time. So here's they. And he talks about these two things. He talks about the theory of algebraic functions, which is what we're doing if we sort of study maps between holomorphic maps between complex varieties. And he talks about the theory of numbers, which is where I spend most of my time. And then he sort of says, sort of sadly, one would be totally obstructed if there were not a bridge between the two. And then he looks kind of sad and pensive, as you see in the picture. But then, just as God defeats the devil, this bridge does exist. It's the theory of the field of algebraic functions over a finite field of constants. So we would say the function field case, right? The situation of a curve over a finite field. And indeed, this bridge of they is what connects these two seemingly disparate stories. So here's how this looks. Oh, I guess, okay, so I meant here I should have written that X is actually over Q, because my sort of part of my game is that I want X to be something which has a realization in characteristic 0 over the complex numbers and also over a finite field. So sorry, this should say X is a projective variety over Q, not over FQ. But what I want to, and again, lots of details swept under the rug, I'm going to presume that it has like a good model, modulo P. And so it makes sense to study the points of this variety, not over the finite field, but over the field FQ parentheses T. That's the kind of field that Vey was referring to when he was defeating the devil on the previous slide. And we're going to look at the algebraic variety of morphisms from P1 to X, the moduli space of rational curves on X. And we're going to look at the points on that space over a finite field. So the key point is that if you think about what a point of X of K is, a point of X over FQ parentheses T, I'm going to be very concrete about it. Maybe I should have put this on the slide. It just literally means like I can assign a rational function in T over the finite field to every coordinate. But you can also think of that as for every T in FQ, I get a point over FQ of my variety. In other words, I get a map over FQ from P1 to my variety. And what's more, this notion of height that I did not define, I promise you that actually what height means for a point over this function field is it corresponds to the degree D maps on the right-hand side. So this variety, now here I have it right, it's supposed to be on Pn over Q. This variety, the variety of rational curves on X, or the variety of morphisms from P1 to X, it somehow can see both problems. And again, I should have written the variety of morphisms over Q, not over FQ, because on the one hand, its phi in characteristic 0 really brings it into contact with the variety of holomorphic maps from P1 over the complex numbers to X considered as a complex manifold. And indeed, it's a little bit confusing. Well, what do we mean by saying like the characteristic 0 fiber is the same as the characteristic P fiber? And what we're going to talk about today, I'm going to mean something very specific. I'm going to mean that there's a relationship between the cohomology of the two varieties. But then secondly, if I look at points on this variety over the finite field, that sees something about the Batyrev-Manin problem, not for the variety over Q, which is, as a number theorist, maybe what we start out caring about, but in this closely analogous question of the other type of global field, it tells us something about the Batyrev-Manin function for counting rational points of bounded height over this global field K, which there's a sort of time-honored tradition that sort of has taken us very far of sort of believing that this gives us good insight into what's happening over number fields too. So this is the bridge, but it wouldn't be much of a bridge if one part of the variety could see One thing about the variety could see this topological question, and the other part could see this number theoretic question. Those two parts of the variety have to see each other, and indeed they do. I mean, that's sort of what the Grothendieck-Lefschetz fixed point formula does. It gives us some relation between the counting of points on this variety and its cohomology. So now I've built the bridge, or at least I've gestured at the bridge, and I'm going to tell you a little bit of something about this, how this works. So the dream of 2005, and I should say, now I look back and I'm like, this is probably a little premature to give this talk in 2005 because we knew nothing. This was something that Akshay and I had been talking about for a while, but there were no theorems, and it was sort of basically what I've already told you is basically like what we knew. But the question is, can you actually get this to prove anything? To prove implications between topological facts about the holomorphic maps from P1 to X and questions about counting rational points. So now I just kind of want to give you a report on what progress has been made in the intervening 20 years. But before I do that, I want to bring up yet one other number theory problem, like a very popular one, which is the problem of counting number fields. So how many number fields are there, extensions of Q of degree n, whose Galois group, but here I of course mean the Galois group of the Galois closure, is some specified subgroup of Sn, some specified transitive subgroup, I should say. Well, again, infinitely many. So now let me say of discriminant the most B. And by the way, by comparison with the Batyrev-Manin question, where it was completely obvious that that was finite, here there's already content in the fact that there's only finitely many such number fields of bounded discriminant. That's an old theorem of Hermite. So it's not hard to understand it, but I want to emphasize that it has some content. But this is a finite set. And similarly, we can ask how it grows with this real number B. And the conjecture, which is made by Günter Mahler, looks pretty familiar, right? Now, I guess one way to look at this is like, there's not that many different functions. So maybe it's just a coincidence. I mean, what's it gonna be like sine cubed? I mean, it's not, but no, I think there is like, I think there is something more there. And again, this is a problem which people have worked on a lot, and some things are known, but much more is not. The set of groups G for which we really know the answer to this question is quite limited. But maybe as an aside, which is not really so much I'm going to talk about today, one way of thinking of this is a degree, a G extension of Q, an extension of Q with Galois group G can be thought of as a spec Q point on the stack BG, the classifying stack with a finite group. And so it's quite natural to be like, well, maybe this is just Batyrev-Manin for the stack BG. And I would now say that that is correct, but the problem is that BG is not a projective variety. And so there's not an obvious notion of height. So that was a project that David, who's here, and I worked on with Matthew Satriano. And there's also a wonderful paper by Darda and Yasuda, which now I think that the theory of height on at least this kind of stack is like on a pretty firm footing. And so it is possible to state a Batyrev-Manin conjecture for algebraic stacks, which sort of incorporates both this conjecture and the sort of classical Batyrev-Manin for varieties that I stated earlier. Just, because when problems are hard and we can't solve them, we just like to make a more general class of problems that we also can't solve, in which those are included. But so you can ask, does this too have a topological manifestation, just as the Batyrev-Manin have this topological manifestation in terms of spaces of rational curves on a variety? And that is true. So I sort of made this sort of square of things where on the top we have on the left, the Batyrev-Manin question about rational points of X of bounded height, and on the right, this kind of Cohen-Jones-Siegel question about what can we say about the topology of the space of 3D maps. The two left-hand things are in some kind of analogy where we're doing some kind of arithmetic counting problem, the problem of G extensions, and then what fills in the fiber square, so to speak, is that we would want to study the topological question of, instead of G covers of Q, G covers of CP1. And that turns out to have a very nice moduli space called a Hurwitz space. In this case, the analog of degree turns out to be the number of branch points. And again, for those who have thought about this, I'm lying in many ways, which I think and hope are inessential to the point I'm trying to make. But you can agree that on the right-hand side, in both cases, we have a family of spaces, which you can imagine get on the top get more and more complicated as the degree gets big, on the bottom get more and more complicated as n, the number of branch points get big. And we're asking sort of questions, you might say, about the asymptotic topology of these spaces. What can we say? But once again, what we have is that this counting function that Mala asks about, once again, turns out to be the number of FQ points over a finite field, on this moduli space. And so we ask what happens as n grows, right? Because then on the left, our discriminant is growing. There's you see q to the n. On the right, in some sense, the complexity of this space is growing. And we try to see what we can say. Okay, in this slide, we're just about a little less than halfway through. So let me sort of sum up everything we did, because I want to sort of now for the next few slides, sort of stop talking so specifically about the Siegel problem and the Herbert space problem, and just sort of say, abstract it out and say, we have a sequence of moduli spaces. Might be maps from P1 to X, might be spaces of G covers, whatever they are. It's some list of spaces that we want to study asymptotically. And we're just going to suppose everything we need. We're going to suppose the spaces are over Q, or it's going to suppose they have good reduction, wherever they need to have good reduction. And then there's two things we can ask. We can ask about a topological question, saying that these xn are in some homotopical sense more and more alike as n grows. They're converging to something. But actually, I am not a homotopy theorist. Some of my collaborators are. So I'm just going to actually use something very modest about this. I'm going to say that what I mean by the fact that these spaces get more and more alike is that their cohomology converges to something. And actually, I think on the slide I have homology, so let me try to say homology. And not even all of their homology, but just their homology with rational coefficients. So I know the real homotopic theorists think I'm like a weakling for restricting to this, but this is sort of natural in this setting. And so maybe what I mean by saying these are topologically more and more alike, and we'll give you an example of this a few slides down, is that if somebody comes up to you and says okay, what's the h lower 5 of this space? What's its dimension? Maybe I don't have to tell you which space I mean. Maybe the first two are different, but maybe after a while it stabilizes. And the answer to what is the dimension of h5 of the space is the same for all sufficiently large n. And that's what we mean by homological stability. That would be a characteristic example of a homological stability theorem. So when I say the spaces are getting more and more alike, all I'm really going to mean for this talk is that the rational homology stabilizes. And usually we'll want it, how big does n have to be? It turns out that typically what happens, and typically what we need, is that we need that to happen once n is bigger than some multiple of I. So it doesn't matter what it is. So I just put 0.0001 to mean some small constant, but I don't care what it is. So if I want to do h5, I just have to let n get up to 5,000. And then after that, the hi is always the same. Okay, so that's the topological side. On the other hand, on the arithmetic side, I'm supposed to be trying to count the number of points on these varieties. So now you might say, well, is that supposed to converge to something? Well, not quite. I didn't say this on the slide, but typically these varieties will be growing in dimension. So certainly, I mean, this is sort of a very elementary heuristic that works surprisingly well, which is that if sort of somebody tells you, I'm thinking of a secret variety, and it's n-dimensional, how many points does it have over FQ? What should you say? You should say Q to the n, right? What else would you say? Maybe if you're really clever, you should first ask, well, is it irreducible? Maybe if that's something, you want to do 2 copies of n or something. And that's I say that to be silly, but also because it's relevant to something I'm going to say later. But roughly speaking, I think you should, if you have no choice but to guess how many points a irreducible variety of dimension n over FQ has, you should probably guess Q to the n. And in some sense, all of these conjectures, when interpreted in terms of counting FQ points in these moduli spaces, again, I'm slightly shoving some details away about these powers of log, but roughly speaking, they tend to say that this variety has a number of points that's asymptotic to maybe not quite Q to the dimension, but at least some constant times Q to the dimension. Right? Because after all, nobody yelled at me, but if I said my best guess is Q to the n, One of you might have said, but like, come on, the only variety I know is like projective space. And that doesn't have q to the n points, right? It has q to the n plus q to the n minus 1 plus q to the n minus 2, dot, 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 dot. But that is at least a constant times q to the n. It's q to the n times 1 over 1 over 1 minus 1 over q. So this is sort of a surprisingly robust fact that actually like happens a lot and is conjectured to happen a lot. But the question is, why are these things related? Okay, actually, I've gone a long time without even giving a single example. So let me just argue that this does sometimes happen. My favorite moduli space, I'll let xn be the configuration space of n points on A1, which you could think of. So it's the moduli space of n distinct points on A1. I like to think of that as the moduli space of square-free divisors on A1. That's a good pretentious way to describe n distinct points. So the FQ points on this variety are simply the set of monic square-free polynomials, right? There's a polynomial whose vanishing locus are those n points. The individual points might not be defined over FQ, of course, because it's unordered. I should have said it's by saying divisor, I'm saying it's an unordered set of n points. On the other hand, the complex points of this moduli space, well, that's just the space. Now we can be a topologist about this. It's the space of unordered n tuples of points in C. And this is a wonderful space, and it turns out that it's an island Lie space at K pi 1 for the Artin braid group. It's easy to sort of, if you imagine those n points moving around and imagine what a loop is in that space, you can kind of see the braids. It's a little harder to show that it's a K pi 1, but not too hard. And indeed, so first of all, this is great because it means to study the cohomology of this space. It's just a group cohomology question. Once it's a K pi 1, we're just saying, like, what is the group cohomology of this group, the Artin braid group? How much pain have I undergone in my life from saying, like, oh, it's just group cohomology at this point? Now, that can be kind of hard. But in this case, it doesn't sound hard, but it is. But in this case, it's been known for a long time. It's quite remarkable. And indeed, the H naught is one-dimensional. That's just to say that the space is connected. You believe that, right? I mean, you can sort of, if I'm thinking of endpoints and you're thinking of different endpoints, the complex plane is a pretty big place. I can sort of get from one configuration to the other without ever having 2 points run into each other. So that's always Q. The H1 is almost always Q, at least when n is bigger than 1. The braid group on one strand is not a very interesting group. It doesn't have very much homology, but once n is bigger than 1, it stabilizes, and then all the rest are 0. So this is a very good example that I think it's a pretty simple space, but it really gives you the flavor of like what homological stability looks like, because you could be forgiven for thinking that these spaces are not at all alike. First of all, it's the nth one is n-dimensional, so they're growing in dimension. They have very complicated pi 1s. I mean, the braid group for a large n is a very complicated group, and yet as far as rational homology is concerned, they're basically all the circle, right? If somebody's like, okay, I'm thinking of a secret manifold, and it has one dimension of H0, one dimension of H1, and nothing else. You're like, it's a circle. And that's sort of morally right. Like, that's sort of like what these things are converging to in rational homology. So just to sort of, and I didn't count the points on this slide, but we're going to do it in a minute. Okay, so I promised a little bit of Grothendieck Lefschetz. I'm just looking, I'm like, is there literally one thing I actually stated completely correctly on the slide in this talk? And I think this is it. I think I did. Oh, no, I didn't, because it should be the size of xn of fq. Okay, so I almost stated one thing exactly correctly, but it's the cardinality of that set that is equal to this alternating sum of traces of Frobenius on cohomology. So this is it, man. This is the place where we relate point counts to something about the geometry of this variety. And now, I mean, let me just sort of say one thing about it. We're going to try to go back and forth between these two sides. And let's just sort of fantasize for a minute. Like, suppose somebody told you at the left-hand side, they said, actually, an oracle came and told me that the nth one of these spaces, xn, it has exactly q to the n points for all q and all n. Like, they're saying, Jordan, your stupid heuristic is actually true on the nose. You would actually know some, you would actually get some geometric information from that, right? You would know, for instance, that this variety, it could not have like a component of dimension n plus 1. Because for large enough q, like that would give you something on order of q to the n points. So that actually, that's an actual contentful geometric fact. In fact, you would be able to, you would know that there was a single component of dimension n, and there was no component of any higher dimension. And if you had some other extra information that told you, for instance, that the cohomology was in the right place, you would even be able to know that the other cohomology was trivial. Maybe I'll just comment, because if you've never thought about this kind of thing before, why do I say you have to know something else? Because maybe the variety I was thinking of was like, I take A2, and then I take one of the points out and I put it over here, and now I have the union of A2 minus a point and a point. Well, that definitely has q squared points over every field. And so, but it's not, it's not irreducible, but it only has one component of dimension 2. So that's the kind of annoying thing that you have to worry about. And then similarly, on the other direction, if an oracle came and told me everything about the topology, or at least about the Étale cohomology, and told me, okay, I'm going to tell you that H naught is one dimensional, and then all the other cohomology vanishes, then this potentially infinite sum on the right-hand side becomes very simple. It's just q to the n, and then I would know some fact about point counts. So I mean, I think what I'm trying to say is, if something that's so good that you would never get a result that good was true on one side, you would definitely be able to draw conclusions on the other side. And now I want to kind of try to convince you that even if what you know on one side is like much more realistic than that, something you might actually under some circumstances know, you can still pass information from one side to the other. And that's sort of how this program works, sort of bringing information between the two sides. So let's see how this looks. I've written Grothendieck Lefschetz again, but I think it's better to really think of this as breaking into 3 separate zones. We're going to break up the sum over the homological degrees, the sum over I, into 3 pieces. There's the big I, which I put last, outside that so-called stable range that I mentioned earlier. There's the sort of small to regular sized i's in the middle, and then there's I equals 0, which is kind of its own. That's a very small I. And each one of those things, if we want to try to analyze it, kind of has its own flavor. So let's talk about how we think of each of those 3 things. And if we can understand all 3, then we can understand the set of the cardinality of the set of points over FQ on this variety. Okay, so first, there's the H naught. Well, H naught is what tracks the irreducible components of Xn. And in the cases of interest, I'll say a little bit about this near the end. It's not as easy as it is for configuration space, where you can sort of see that space is irreducible, but it's manageable. It's often something that you can prove in a combinatorial way. That's what happens in the Herbert spaces. It's often something you can prove by studying some monodromy group. Maybe I didn't put a slide of this, but to give you an impression, if I have some base space and I have a cover of it, and you want to know if the covering space is irreducible, that's a question about the monodromy of the cover, right? It's a question of whether it's a transitive subgroup of the sheets. So you should think about big monodromy as saying that H naught is small, and that we know that big monodromy theorems are a kind of theorem that you will prove a lot, and that's sort of what goes into understanding the H naught. Okay, that seems kind of reasonable. The middle-sized I, in most of the theorems I'm going to talk about today, that's where the hard work really lives. Because if you remember this range of I between 0 and 0.001 n, that's where you hope that you have some homological stability theorem for your spaces. And if you do, then you're in business, because then somehow you know that whatever this is, it doesn't actually depend on n very much, except insofar as there's sort of some multiplier which comes from the fact that if the homology that's stable, you got to switch over to complex and supporting cohomology. So let's not worry about it too much, but like roughly saying this part is the same for all n. If you have some topological theorem, which is like where the hard work is what we need to prove. But I still have like 0.999 of the sum left. And here is where you just kind of hope that you have some pretty soft argument that gives you some crude upper bound. But then, as you know, if you've ever sort of worked with conjectures before, somehow the higher you go in homological degree, this is supposed to contribute less. So maybe this contributes like whatever the Betty numbers are, times q to the minus 0.0001 n, and that is a pretty slowly diminishing function, but it is negative exponential, so that's enough. So you hope that something very crude allows you to like totally control that part and mean that you can ignore it. But actually, I mean, there are situations where you just can't do that, and then like you can't even start. So I mean, the famous question, I know Johan likes this question about like how many FQ points are there on MG? There, like the cohomology past the stable range is like completely huge, and we have like no control at all. And still, it would be incredible if somebody had an asymptotic for how many genus G curves there are over FQ. Do you think there is an asymptotic, Johan? What do you think? Yeah, me either. Okay. I don't know if anyone in 2005, nobody had any idea, and like also now. So if all this works, it turns out that you get what you want. You get that the ratio of the number of points in this variety over q to the n actually approaches a limit. And maybe I should say, because one of the many lies I told in this slide is that I said you get this middle part you get from a homological stability theorem. You need a little bit more. You can't get by with just a topological theorem. You need the trace of Frobenius to be the same. So this is something Aaron explained to me how to prove, in many cases relevant to this topic. You need something to be Frobenius equivariant. So that certainly goes into this too. Okay, so what I'm going to do sort of for the last part of the talk is basically give you a huge spray of progress that people have made on this kind of problems. But when I was thinking about preparing this talk, there's sort of three kinds of theorems. There's sort of three levels of knowledge you can have, which I'm going to call level 1, level 2, and level 3. And level 1 is all you understand is the H naught. You have the sequence of spaces, and at the very least, you can sort of, maybe you prove monodromy theorems, you do something, but you can understand the connected components. And even just knowing that, you can really get some content. You can say, if I let q go to infinity first, I can compute this limit and see what it is. Okay, if you know a little more, if you know a homological stability theorem of the type that I gestured at, then you can show what you really want, which is that the limit as n goes to infinity exists. If you remember back to the beginning, like when we were talking about Batyrev Manin or talking about Mala, like, you know, q to the n was our bound. We were trying to let the discriminant grow or the height grow. And so that's what letting n goes to infinity does. And that's what you can get if you have homological stability. You can get the existence of the limit, but you don't know what the limit is. So that would be kind of like the Batyrev-Manin conjecture before Peach, where they were like, we believe that the order of growth number of points of bounded height is b to some power times log to some power, and then Peach predicted the exact constant. And finally, level 3 is that if you actually know not just that the homology stabilizes, but what it stabilizes to, and if you had the full flowering of like Cohen, Jones, Siegel theory, you would have that, because you would say, oh, everything is converging to like the double loop space, some space, and then I'm not a topologist, but like, you know, Kirsten knows how to compute the cohomology of that space. I mean, people who know how to do topology know how to do that. So those are the 3 levels. And maybe I'll sort of show you how those play out in the simple case that I mentioned. So again, I told you that this space, the configuration space of A1, it's the space whose FQ points are the number of monic square-free polynomials. And q to the n is the number of all monic polynomials of that degree. So this ratio is the probability that a random polynomial is square-free. So again, let's look at the 3 levels of knowledge. I told you that H naught, I told you that this configuration space is connected. That tells you that if you let q go to infinity, the probability that a random polynomial is square-free goes to 1. That's not such a hard fact, but it is true, right? I mean, you sort of, it's square-free if only the discriminant vanishes. That's sort of some closed locus. So of course, like the probability goes to 1 as q goes to infinity. The homological stability tells you that there is a limit as n goes to infinity. So this question of like, what's the probability random polynomial is square-free? That has like an actual answer. It converges to something as n goes to infinity. And finally, in this case, as I said, Arnold actually computed what the stable cohomology is, and that tells you what the limit is. This tells you that it's 1 minus 1 over q, which is indeed the probability that a random polynomial over q is square-free. I want to emphasize this is like the most difficult proof imaginable of that fact, which you can prove rather readily by analytic number theory means. But I mean, it's sort of a picture to sort of show how the method works in a very simple case. And now I'm going to sort of give you a lot of people's names and a lot of stuff that has been done to show that this actually can be pushed through in many non-trivial situations. So this started with work on the so-called Cohen-Lenstra conjectures, which we think of as a conjecture about I think when Cohen and Lenstra framed it, has been much generalized for the years. They framed it as a question about what is the class group of a random quadratic field? One of the founding questions of arithmetic statistics. It turns out that this is actually a consequence of Mala's conjecture. It comes from what you get if you count extensions of bounded discriminant, where G is a dihedral group or a generalized dihedral group. So like a semi-direct product of Z mod 2Z by some like Z mod LZ to the N. I should say that there was already prior art, including by Jeff Actor, who's here, and Jukang Yu, who proved big monodromy results that get you what's called sort of the level 1 knowledge. And so the sort of what happens in the large Q limit was like already understood. And then what Akshay and Craig and I were able to do was to prove a homological stability result for these Hurwitz spaces. So do you all remember the levels? That's level 2. We proved homological stability, and that gave a kind of weak Cohen-Lenstra conjecture where there was all these arithmetic statistical things which were conjectured to have a certain limit. We couldn't quite prove that they have that limit, but we proved that they had a limit, and moreover, that the larger Q was, the closer you were to the predicted Cohen-Lenstra limit. In later work with Craig and with his student Tran, we extended that to some extent to more general G in a way that gave upper bounds for Mala. But quickly after that, as a wonderful breakthrough paper by Aaron Landesman and Ishan Levy, which get all the way to level 3, and for a rather general group. And there are some caveats, but to the extent that Mala's statement is correct over FQT, I think that's basically proved in their papers. That's a very satisfactory story about what happens with Hurwitz spaces. I do want to emphasize, I want to say one thing about level 1 knowledge, which is that it's quite useful in the sense that, like, if 3 people are arguing about what the probability is that a random polynomial is square free, level 1 knowledge only tells you what happens as Q gets large, so it can't tell the difference between like 1 minus 1 over Q and the reciprocal of 1 plus 1 over 1 plus 1 over Q, but it can definitely tell the difference between both of those and 1/2. It can definitely tell you, as I showed you, that like as Q goes to infinity, you go to 1. So in some sense, like a lot of conjectures in arithmetic statistics, I didn't really emphasize this when I talked about Batyrev, Manin, or Mala, but one interesting thing about those conjectures is that they were certainly both incorrect as originally stated. It's very subtle to get them exactly right. And I think this level 1 information is actually quite useful for stress testing any conjecture of this form, because a lot of them, the reasons that they are incorrect sort of could have been understood at this very level 1 level. And in particular, Melanie Wood has a wonderful paper where she basically gets level 1 information for every Hurwitz space, for every finite group. And as a result, in this kind of vastly generalized story of non-abelian Cohen-Lenstra heuristics, so not just class groups, but what does the maximal unramified extension of a random field look like, by Yuan Liu and Melanie and David Zurich Brown, that conjecture is kind of stress tested in the function field case by like comparing it with all this level 1 knowledge and showing that it's compatible with those things. So another really wonderful, very recent development comes from the fact that, again, in the interest of time, I sort of talked about counting points on a space. I phrased Grothendieck Lefschetz as we're counting points on a space and comparing that with the homology of the space. But of course, Grothendieck Lefschetz is much more general than that. You could take any local system on the space and compare the sum of the traces of Frobenius and the stalks with the cohomology of that local system. That's what we call working with non-constant coefficients. And by doing that, another wonderful recent paper is by Bergstrom, Diaconou, Peterson, and Westerlund, who are all, I guess, 3 topologists and a number theorist, using topological input from a bunch of other people, Miller, Potts, Peterson, and Oscar Rendon Williams. Boy, there's a lot of names in this slide. They prove the famous random matrix-oriented conjectures, also by many people, about what's going on with the moments of the central values of L functions. And it turns out that that comes from proving homological stability, and in fact, computing the stable homology, not of the Bray group with coefficients in Q, which is what I told you about from Arnold, but by being able to compute that with coefficients in representations of the Bray group, which you get from Schur functors applied with Burau representations. So that's another example where you get and I guess I should have said, oh yeah, I say it. Okay, so it's they prove these conjectures over FQT, exactly matching these predictions via a homological stability result. Let's see how much time I left. Okay, I'm almost done. So I'll say like Mark Schusterman and I have a new paper about questions about prime discriminants, again, something that seems completely out of reach for in the number field case, but which we can now prove using sort of some cleverly chosen coefficients for these spaces. I should say in Siegel's original paper, he didn't just study maps from P1 to PM. He actually studied maps from an arbitrary Riemann surface to Pn. So like, I'll comment that that works in this setting too. So in my paper with Aaron about summer groups, we need to, and so do, sort of show that you can get this to work where you have maps from a fixed curve of genus G with n punctures, like to the target. Maybe even though we're near the end of the time, I will stop and comment because this is an algebraic geometry conference. One thing that is not in this whole story is MG. I would like it to be there, but it's not. So I'll emphasize that I think, Ravi, tell me if you agree with this. I think usually if you were like, we're going to study maps from genus G curve to a target, you would have in mind like a whole space like MG of X where the curve varies. Oh, that's going to be your talk. Okay, great. This is an advertisement for Ravi's talk. So that's not in the picture. This is more like you fix the genus G curve and study maps from that particular curve to X. That whole story should have an action of the mapping class group on it, which we know nothing about, which I would like to understand. So maybe Ravi understands it and he'll tell us about it later today, right? No? Okay. You've disappointed me again. So to close though, did you guys notice that I started with one problem and then we completely forgot about it because I started talking about the Mala type problems instead? It turns out that they're easier. The topological problem for maps from P1 to X, I think is still quite hard. We don't have K-pi1s lying around, and we can't reduce to group cohomology problems. So maybe I was inspired by something Mike said yesterday. It's very much this problem that Mike said, that it's hard to understand what conditions on the topology are placed by a map being an algebraic map. Whereas for covers, by the Riemann existence theorem, a branch G cover of the disk is the same, whether you mean that, you're talking about the same thing, whether you're talking about it algebraically or homologically. For maps from P1 to an arbitrary target, we have no such assurance, and so it's very hard to understand. And actually, what's interesting, because the topological problem is so hard, there's actually been some movement in the other direction, which I also didn't talk about until the end. So I'll just comment, there was a wonderful talk, I hope you all went to it, Sho Tanimoto's talk yesterday about this wonderful work with Ronald Doss and Brian Lehman and Phil Tosteson, with key input from Will Sawin and Mark Schusterman, where for Del Pezzo's degree 4 over function fields, they prove both the Batyrev Manin conjecture and homological stability for maps from P1 to the space. But not deriving one from the other, which is what I've been talking about today, but actually by sort of devising a proof that somehow, although it's talking about two different things, is sort of in some sense the same proof on both sides. And then I'll just close by commenting, okay, let's see if you remember. At the very beginning of this talk, when I gave you my two lists from 2005, the list of types of varieties for which we know Batyrev Manin was a little bit longer than the list of types of varieties for which we knew Cohen, Jones, Siegel, because there were the ones you could actually do by like good old hardcore British style analytic number theory, the circle method. They were like the very low degree, very high dimensional varieties. And so that's the one case where somehow you actually know more on the counting side than you do on the topological side. And in fact, analytic number theory is so good that and it gives you such good bounds on the point count that it actually puts you in that sort of slightly unrealistic situation where you can derive some actual geometric information from it. So this kind of starts with the PhD thesis of Thibaut Bougan back in 2011, but there's wonderful papers by Tim Browning and Pankaj Vishay, Tim and Will, Jakob Glass and Matthew Hassel-Liu, who's here, where the information you get about point counting is so strong that it actually allows you to get information for the earlier papers in this list about the irreducible components of the space of rational curves in a variety, which, oh, and now I forgot the authors, Robbie probably remembers. I mean, for a very general hypersurface of very low degree, Joe and some other people, I forgot who's on this paper, you can prove that the space of rational curves is irreducible for very general hypersurfaces, but this gives you for all hypersurfaces. And now with these more recent papers like Jakob and Matt's paper, you can even get information on like the dimension of singularities of those spaces, like quite refined geometric information, like because you know so much about the point count. So this is sort of a class of examples where the information flows the other direction from number theory back to topology. So so that's it. That's 20 years of work by like a lot of people. I hope I've given a good account of it, and I'm gonna stop there. Thank you guys so much.
Hey, thanks for the talk. You sort of gestured at this on, I think it was the slide right before this, that when you're outside of the K-home situation, the topology is going to be more manageable. But what type of spaces XM would you expect homological stability for? Just like zooming out is the force picture of this.
I mean, certainly, I guess, given the philosophy from homotopy theory, I would expect it for spaces of rational curves of higher and higher degree on a Fano variety. That would be wise. That's certainly homological stability is certainly like broader than that. I'll give an example of a space where I think we don't know, but which is very natural. Like, we don't know that much about the moduli space of elliptic surfaces. So you could think of that as like the space of maps from P1 to M11. I know this is something Aaron and I have talked about a lot, but I think we just don't have that homological stability theorem, right? And I think it's very reasonable to expect it. Again, do you agree that it's reasonable to expect it? Okay, yes. So that would be an example that's like beyond the boundary of what we know. And it's a very natural space. Like Hom D from P1 to M11 is like moduli space of elliptic surfaces with a certain number of bad fibers. And I think that's an example where we know nothing and it would be very arithmetically interesting to know something. If Park is here, he counted points on that space. So I should have put his name on a slide too. I don't know if he's in the room right now, but another, yes, okay. So you counted points in the space. We don't know the homological stability, right? What? Oh, good thing I didn't make a slide about this. How many people can I insult with like one statement? How many people whose work can I obviously not know? Okay, we'll talk about it after. Sorry. Okay. Does anybody have a question I do know the answer to? Yeah.
So, I mean, how you starting to want to build some sort of structural kind of scanning map? Is it true that theory doesn't consider structural or something like that?
Wait, I thought I said I was going to get a question I did know the answer to. So I will say, I am not the homotopy theorist in any of my collaborations, but certainly the scanning technique is when you do know the stable homology, that's often how you get it. And maybe I should say, because that reminds me to say, like, especially for the younger people in the audience, like, one part of the story I didn't tell that happened between 2005 and now is that actually, like Craig and I thought that we had done that for the Hurwitz space, and I gave a talk about it at the joint meetings and everything like that, and it was like completely wrong. So just for the young people, just know that that can happen, and you just really confidently say something in front of a lot of people that's like completely wrong, and then you realize it's wrong, and it's like you just got to face up to it and deal with it. And that was like already more than 10 years ago. It's okay. So just it will, some number of people in the room, it will happen to you at some point. So just be aware that it sucks, but then you will like live and get through it. Okay. So thanks to Aaron for actually proving that theorem. So it is true. So fortunately, the theorem is true, but if we didn't prove it.
I wanted to ask, because you said something about the analogy between rational point over number fields and the rational point over function fields.
Yeah.
You could also imagine doing higher genus function fields, which would maybe be more related to higher genus curve for your variety. You know, there are very few of those. Can you comment about, is there anything you could say about this?
Well, okay, let me separate two things, because I think changing the function field to be a higher genus function field is not so different. That's like working over a different number field instead of Q. But that's like sort of changing K. Changing X to be something like a higher genus curve, or more generally some general type target, then I think somehow both sides would kind of break down, because on the rational point side, you just wouldn't have very many rational points, or maybe they would be supported on some closed subvariety. You would just study that instead. And then on the topological side, you just wouldn't have very many spheres on it. They too, I suppose, would be like localized on some part of the variety. So I think somehow you wouldn't expect the stability on either side in that case.
I mentioned that there's some general techniques to show Frobenius variance.
So I think it's various places now, but you can see it in the appendix that Aaron wrote to our joint paper. But roughly speaking, the way you should think of it is that, so first of all, why is it hard? The reason it's hard is because when you prove a homological stability theorem, you usually have like some map from one space to another, and then you prove that map induces an isomorphism on homology in some range. And the problem is that the natural maps you do, I mean, when I started working with Craig, I gotta say, it's very freeing for algebraic geometers like us to work with topologists, because they're like, yeah, you just like glue this thing onto this thing. I'm like, they just do it. Like, they don't worry about whether it's algebraic or not. They're just like, look, you have it, this thing, and their ends have the same shape, so you can just stick them together. Okay, so when you do stuff like that, it works in topology, but it's not quite algebraic. So it's a priori hard to show that it does that it has a manifestation over a finite field at all. But I think if you sort of think of things properly and like say the word log enough times, I mean, you actually can do things that are like gluing two things together in the algebraic category. And then once you sort of set everything up properly, like it's sort of, it's just one of those Grothendieck moments where you sort of define everything correctly enough that it automatically commutes to the Frobenius. But it's some real work.
So you use the connectivity of the configuration space over C to show that the limit as Q gets to infinity of the squared phase probability of the monoclonal squared free goes to 1. A more interesting number than 1 is the number of real components of the configuration space. You interpret the number of real components of the configuration space as something to do with that probability of space, not a polynomials, something.
Yeah, so let's think. Can I do it in my head and on the fly is a question. So usually what happens is, so let me repeat it if people can hear it. So Kirsten's question was about some others richer stuff that goes on topologically over algebraically closed fields, and it actually ties in very nicely to the talk that you're going to give. And you know the real configurations, there's like n factorial different components, because on the affine line over R, you just can't pull one point past each other. Like in a component of that space, it's fixed. So I can't do that in my head. I can say, I once wrote a blog post about how this works for like why that number of components of something gives you like the number of acyclic orientations of a graph or something. Like I once thought about this, like wrote something down. There's this nice formula for the number of acyclic ways that you can direct a graph that has to do with the number of components for a hyperplane component. So maybe it's like, oh yeah, I can see it. Okay, ready? The complete graph. If I want to put a direction on each vertex to make that acyclic, it has to be a complete ordering of the vertices, right? Like it has to tell you what order the vertices come in from start to finish, and there's n factorial ways to do it. So I think that's what it is.
probability squared for polynomials, and that was a fun way to see that probability. But we have other topological invariants related to that configuration space, and they give more interesting numbers. Question is, can you say something? You know, q goes to q minus 1. It's a little bit like root of unity goes to. I can start, but I don't know the answer to this question. Yeah, what can you do with the real problem?
Yeah, I think, okay, I really can't do it in my head, but I think what I would say is it will have to do with thinking about the action of complex conjugation on homology. Instead of thinking about the action of Frobenius, think about the action of complex conjugation. And that will somehow, I don't know if that will have all of it, but that will have some of it. Sorry not to have a better answer, because it's a great question.
Well, looks like there are any other questions. Thank you so much, Jordan. And let's meet back here at 2:50.